Okay, so we've spent the last several lectures talking about compact sets. And I'm going to, okay, cool. Spend the last couple of lectures talking about compact sets. And today what I want to do is say a little bit more about compact sets. In particular, I want to talk about something called the Cantor set, which is a very interesting subset of the real line. And then I want to talk about connectedness. And what does it mean for a set in the reals or in any metric space to be connected? Okay, so those are the plans for today. I just want to have you recall from last time, we concluded our time by discussing a theorem of Cantor, which basically says the following. Had to do with an interesting property known as the finite intersection property. So the theorem said if you have a bunch of compact subsets, let's say K sub alpha, are compact subsets of some metric space, X, and let's say that you have the certain property that's true. If any finite subcollection of these sets has a non-empty intersection, then in fact the intersection of all the sets is not empty. So this is what's known as the finite intersection property. Sometimes we'll just abbreviate this by FIP, the finite intersection property. And it's true for any collection of compact subsets of X. Okay, and we proved that last time. And in particular, a very quick corollary that we mentioned last time is that suppose all these are nested compact sets. So let's suppose you have Kn, a sequence of compact sets. You have a sequence of compact sets that are nested. Then, in fact, the intersection of all these sets is not empty. So intersection of Kn, n goes from 1 to infinity. Now, what does this mean? This intersection means basically look at everything that's in all the sets. This actually has something in it. I'll just say non-empty. Okay. One thing I want to mention today, which I did not mention last time, but partially answers a question that Jenny asked last time, is what is the connection with closed sets? Is there a characterization of compact metric spaces or compact spaces and closed sets? The usual definition of compactness involves open covers. But there is a characterization of compact sets you could take to be the definition if you wanted that talks about closed sets. Compactness and closed sets. So that's the following characterization. It's a theorem. So a space X is compact. Turns out this is equivalent to the following condition. It's equivalent to saying that any collection of closed sets let's say I call these sets D sub alpha, satisfies the finite intersection property. This turns out to be equivalent. What is the finite intersection property? Finite intersection property says if every finite subcollection has a non-empty intersection, then they all do. Okay, so maybe I'll rewrite that here with the emphasis here that if maybe I should put the emphasis on every finite subcollection has non-empty intersection. Then the intersection of all the sets is non-empty. So what does this mean? So if we have a collection of closed sets that has the finite intersection property, and if that's true for any collection, then X is compact and vice versa. And let's just make sure that I wrote this correctly. So X is compact if and only if any collection of closed sets, any or every collection of closed sets, satisfies the finite intersection condition. If every finite subcollection has a non-empty intersection, then they all do. So let's just see why this is true. So the forward direction is pretty trivial based on what we've shown already. Why is that? Well, what are we going to choose to be our compact subsets of a metric space? We're going to assume that X itself is compact, and maybe we'd like to use that theorem up there. So you give me a collection of closed sets, and I want to show that it satisfies a finite intersection property. Then what sets will I use in that theorem if I want to apply that theorem? Well, let's look at this theorem says look at a bunch of compact subsets of some metric space. And then the claim is that it satisfies the finite intersection property. Yes? Okay. Well, now I'm starting with a collection of closed sets. That are as in that theorem. And then I want to use something I already know, namely that is true. So what would you like to use? Here this says talks about a bunch of compact sets. These are closed sets, aren't they? Ah, yes, they're closed subsets of a compact space. So they are, in fact, compact. Okay? These are closed subsets of a compact set, space X. So they're compact. And now we can just apply the previous theorem, right? Apply previous theorem. Okay. Everybody happy with that? Okay. Now, I claim the reverse is also true. And I think I'm not going to prove this, but I'm going to let you do this. So you can have fun with this. This is an exercise. Okay, so if you have the case that any collection of closed sets satisfies a finite intersection property, then show that X is compact. Let's just talk through how the proof might go. How would you start a proof like this? Let's see. I want to show that every cover, open cover, has a finite subcover. That's what I want to show. I want to show this side, yes? So given an open cover, can I use this somehow? Given an open cover, are there any natural closed sets to look at? Yes, look at the complements. So given an open cover, look at the complements. The complements are a bunch of closed sets. And then your job is then to, well, you know that this closed set should satisfy the finite intersection property. right? So that's the connection that you would use. Okay. Now, of course, if you're trying to show that this implies this, you could also show, another strategy is to show that not this implies not this, right? Okay. And so that's another way to go about it. If you want to show not this implies not this, then then what would that mean? That means there is an open cover with no finite subcover. Yes, you could start with that. Well, what would that mean? Well, maybe you could produce then a conclusion here. So you look at the complements. Those are closed. And if this is a cover, then the complements basically should have an empty intersection. Okay, and so that would be the way to proceed. So I'm just going to let you think about this as an exercise. But what you see is there is a way to do compactness just looking at closed sets. Okay. Now, there isn't a closed cover characterization of compactness, and that should make sense to us because, you know, points are closed in metric spaces, yes? So if you were to demand a space to have the property that every closed cover has a finite subcover, you'd really just be demanding that the space is finite, which is a little too strong. Okay, it's already just saying something that you already want. And then if you said, okay, well, let's just rule out points. We don't allow those in our closed cover characterization. Well, then what are you doing? You're really taking a point and you're allowing a little interior ball around it, right? So you might as well use open covers. Okay. So you can't expect to have a closed cover characterization, but there is a finite intersection property characterization of compactness. Okay. Let me look at another consequence of this theorem, or in particular this corollary, and that is a beautiful construction known as a Cantor set. So a Cantor set looks something like this. What I'm going to trace for you is a description of how to construct the Cantor set. But I actually can't draw the Cantor set. It's too hard. Okay. But you'll get a very good idea by looking at this picture. Start with the interval 0, 1. Okay. And if you don't mind, I'm going to call this set K0. And now what I'm going to do is I'm going to construct another set, which is basically the first set where you remove the middle third, like so. So this now is actually at the point 1/3 and 2/3. Are you with me? Okay. Remove the middle thirds, and I have how many intervals? 2. Good. Suppose I now, from these intervals, remove their middle thirds. How many intervals will I have? 4. And what will this where will this go? From 0 to 1/9, 2/9 to 3/9, 6/9 to 7/9, and 8/9 to 9/9. Are you with me? Okay. That's K2. What do you think K3 is going to be? Remove the middle thirds, right? So now we have gone from 1 set to 2 sets to 4 sets to 8 sets. Okay. What can you say about each of these sets? And I can continue to define this construction as so. Okay. So K sub n has how many intervals? 2 to the n. But in any case, finitely many. Yes? Okay. Are these sets closed? Yes, they are the finite union of intervals that are closed. Yes? Are these sets compact? Yes, because they are closed subsets of a compact set, which I know the interval to be. Yes? So what I want you to notice are, oh, this is so cool, K, N they're closed, and in fact they're compact. Okay? What else? They are, they're not open because if you take a point at the end point, it is not an interior point. Okay? But what are they in relation to each other? Nested. Ah, okay. So their intersection is non-empty. Well, you probably could see that already. Can you see some points that must be in every set? Name one. 0. Name another. Name another one. 1/3, 1/9, 1, etc., right? Okay, endpoints of intervals are definitely still in here. Let's try to draw this set. Oh, I don't know. What do you think the intersection of these sets is going to be? So this is what I'm going to call the Cantor set. Let's call this Cantor set. I'll call this C for now. Is the intersection of all these k sub n's for all n. And it looks like this. In fact, of course, this construction was made, 100 years ago. But with the advent of computers and computation, we've actually such sets actually pop up in very natural ways. For instance, this has a very fractal-like structure. This is the language we use today. Okay, if you've ever seen pictures of so-called strange attractors in physics, they look very much like Cantor sets of trajectories. Okay, but what is this set, and what's so special about this set? Here's a question. How many points are in such a set? There are infinitely many. You probably could see that because at least all the thirds or the ternary 1 over 3 to the n's or k over 3 to the n's are in there, yes? Are there more points? Are there any points that aren't intervals? Aren't the endpoints of one of these intervals? How many people say yes? There are more points than just endpoints. How many people say no, just endpoints? Okay, everybody form an opinion. I want to understand this Cantor set C. Are there any other points besides endpoints? We've already decided 0 is in every set and therefore in C. We decided that 1/3 is in every set and therefore in C. Are there any points in here that are not endpoints of intervals of one of these stages? How many people say yes? How many people say no? Ooh, more no's than yeses. Let's find out. What else can we say about this set? Are there any intervals in it? No? Are there any interior points? How many people say this set has interior points? How many people say it has no interior points? Okay, that's probably a little more easy to rationalize anyways. Yeah? Why? If it had an interior point, how could you show it has no interior points? Well, eventually, any such interval gets cut, right? So it doesn't have any interior points. But let's answer the first question, since half of you seem to think there are more points than just endpoints, and half of you seem to think there are less. Here's a question, actually. I'm going to ask you one more question. Those of you who think that there's only endpoints of one of these only stage endpoints appear here, if that were the case, how many points would there be? It's infinite, sure. Countably many. Would you agree? Because it's the countable union of finite number of endpoints for intervals. Yes? Okay. But let's see what we can see here. So here's an interesting thing. I claim here's one way to understand the Cantor set. So let me just summarize some of the things we've just noted. C is closed. Why is it closed? It is the what? Oh, sorry. No. Why is these dots closed? Because it's the Intersection of arbitrarily many closed sets, right? Because it's the intersection of closed sets, right? Okay, great. We see that. Here's another fact about C. C is, in fact, has a property that the book calls perfect. A perfect set. What is a perfect set? Perfect set means it's closed and, anybody know? Every point is a limit point of C. Every point of C is a limit point of C. Okay, so what does that mean? Any point here can be approached by other points. No point is isolated. Yes? By the way, can you think of any of other perfect sets besides this one? How about the closed interval? Every point is a limit point. Yes? And it's closed. All of R is a perfect set. Okay, so lots of perfect sets, but this one's interesting because it's perfect, and in fact, it has no interior, which we'll come to in a bit. Okay, but I haven't justified why every point is a limit point. But I claim this follows from the following insight, which is perhaps the best way to think about a Cantor set. I claim that C consists of real numbers that have a certain property. When you write the real number in ternary, right, not decimal, not binary, but in ternary expansion, then it only will have zeros or twos in its ternary expansion. So whose ternary expansion contains, I heard that, I'm coming, contains only zeros or twos. So let's do several examples, including Bonnie's example, 1/3. Oh, it wasn't Bonnie? Oh, it was Jenny. Oh, okay. Well, we'll still do it. Okay, so check this out. What does ternary expansion means? It means divide into, instead of powers of 10, divide using powers of 3, right? So if I, in ternary, in binary you only use 2 digits, 0 or 1. In decimal you use how many digits? 10, 0 through 9. In ternary you use 0 through 2, okay? Would you agree that all the points in this interval, we'll get to 1/3 in a second, begin with 0? In other words, there's 0 over 1/3 plus, so ternary would just write things in powers of 1/3, 1/9, 1/27, 1/3, 1/9, 1/27, etc. Okay? And I claim all the things in this interval begin with 0 in their expansion, except possibly its endpoint, but I'll come to that in a second. Yes? Then these begin with a 1 over times 1/3. And these begin with a 2, because they're 2/3 plus something, right? Similarly, for the second decimal ternary place, this would correspond with 0. This correspond with 1. This would correspond with 2, yes? 0, 1, 2, 0, 1, 2. Are you with me? Okay. And so if I want a point, let's say in here, I claim that all the points in here begin with the ternary expansion 0.022. All these points in here begin with 0.022, ... which there might be something else, right? You with me? Okay. So ternary looks something like this. Cantor set's one of the coolest things, I just have to say. So let me just write ternary. So ternary would be something like this. Write everything in powers of 3. So for decimals, for these such things, it might be, it's a sum of ak, 3 to the k, where k could go from any integer, minus infinity to infinity. And so we write this as, something like this, a0 dot a minus 1, a minus 2, dot, 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 and then the other digits go the other way. Here, this is the expansion. Okay, goes both ways, but we're only looking at going this way. Okay. Now, what about 1/3? I claim 1/3 can also be written in ternary with only 0s or 2s in expansion. Do you both buy that? Yes? Tell me how, Julian. Oh, sorry. Oh, who said yes? Willie. Excellent. Yeah, so even 1/3 is point, you can see this here. It's 0, 2, 2, 2, dot, dot, dot with a bar over it. Okay? Just like in decimal, 0.9999999 is really also the same as 1. Okay? These representations are not unique because 1/3 could be written like this, but it could also be written 0.10000, dot, dot, dot. Okay? With me? Now, the only ones in decimal that are not unique are the ones that end in all 0s or all 9s, right? Because one could be turned into the other, right? The only ones in ternary that are not unique are the ones that end in a string of 2s or 0s, right? If you want to change 2s into 0s, you increase this to a 1, but then, of course, that violates the rule. So really what I'm saying here is you can always write them. You can write, has an expansion that contains only 0s or 2s. Yeah, I won't change that, but which has a ternary expansion containing only 0s or 2s. Okay, great. Now, what does this mean? Well, I claim this means that you can see the answer to the question. How many points are there in the counter set? Uncountably many. Why? Yes, it's exactly the same argument. Cantor's diagonalization argument would work here. So this shows us, if you see that this is true, what this shows us is not only does it show that every point is a limit point, it shows that C is uncountable. So it also shows that C has non-endpoints of non-endpoints of Kn points. Right? For instance, what's a point here that's not an endpoint? Dylan? Well, I actually don't know what 1/4 is off bat in ternary, but okay, 0, 2, 0, 2, 0, 2, dot, dot, dot. Would you agree this is never an endpoint? What are the only endpoints? The endpoints are the ones that actually they either end in they end in all 2s, don't they? Right? Right? Or a string of what? Well, if they end in a string of 0s, then there's a 1 preceding, and or a 0. I guess a 0. That's right. Yeah, it could be all 0. Or it's 0. So there's lots of non-endpoints. It's uncountable. Just use the same diagonalization argument. So there are way more points in here than you might imagine, right? There's lots of inaccessible points. They're points you can't reach, right? Okay, by being at endpoints. What else can you see? Does it have any interior points? No. What would it mean to be an interior point? Well, you can convince yourself that no matter if there were an interval around it, that around a point in the set, then some of those points would have to have ones in their decimal, in their ternary expansion. Okay? Every point is a limit point. Why? Well, isn't it the case that no matter what number you give me, I can write this as a limit of a bunch of numbers that only have zeros or twos in their expansion? Wouldn't you agree that this, for instance, is the limit of 0.0, 0.02, 0.020, 0.0202, ... Yes, every point is a limit point. Okay? So it's very, very interesting set. Question. So saw a question here. Bonnie. Oh, because K0 is the set of all numbers which have a ternary expansion in the zeroth place, where A0 is either 0 or 2. K1 is the one where A minus 1 is either 0 or 2. K2 is the one where A minus 2 is either 0 or 2, etc. Then we're intersecting them all. Leon. No, because yeah, so I guess I'm defining all these to be always zero. Yeah, from A1 onward, I'll make them all 0. Okay. Yes. Not only is it a limit point of points in the real line, it's a limit point of points in C.
But what if it had a finite ternary expansion?
Oh, if it's finite, then that's an excellent question. That's an excellent question. So what if C every point is a limit point? Okay, now I've convinced you in this case. But what if it's finite ternary expansion? If it's finite, then it's gonna end in something, right? Like 0. Let's say 0, 2. There, that's finite, right? Well, I could write this as a limit of 0, 2, 2, 0, 2, 0, 2, 0, 2, 0, 0, 2, and send that last digit 2 off to the right. Okay. Happy with that? So Cantor sets are interesting. Yes, Emil. Why do we include the endpoints? If we don't, then this would be open. Well, I can't stop you from defining the Emil set to be a construction where you only use open intervals, but you'd have a harder time showing lots of things. So, for instance, of course, now that you have this insight, you can see it, but it's not obvious at first that the intersection is going to be non-empty, right? The intersection is not necessarily open either, right? Because the arbitrary intersection of open sets isn't necessarily open, right? I mean, you could. It's a great little fun project to figure out what you could show about such a set if you opened everything. Okay. Excellent question. Yes, Willie. Yes, but why would I not want to use the ones? Oh, right. Yeah, because I'm trying to show that's a limit point of C. Every point in C is a limit point of C. Okay, excellent question. Okay, yeah. So Cantor sets are really really great. Here's another property of Cantor sets, which is underappreciated. Underappreciated. Another property of Cantor sets that's really quite neat is that Cantor sets are there's lots of properties that are cool, but here's another one. Cantor sets are totally disconnected. course, now I have to define connected, so I'm going to do this. I'll define what this means soon. But the idea is that there's no connect. You give me 2 points, I can find a disconnection that'll separate these 2 points. And I'll have to make that notion precise very, very soon. Okay. What else? There was something else I wanted to say, and it just slipped my mind. What else is true about Cantor sets? It just completely vanished. Cantor sets. Oh yeah, this is cool. How long is the Cantor set? What do I mean by that? Well, what does it mean to define the length of a set for sets that are really strange like this one? One way you could define the length of a set is to ask, what are the lengths of possible intervals that cover this set? Okay? And then take the infimum of the sums of those lengths, right? You've already shown that closed intervals, you can only have countably many disjoint intervals, right? So you can talk about the sums of the lengths of closed intervals that cover a set, right? That has a certain length. And then do so for all such closed intervals that cover a particular set and take their infimum, and you could use that to define the length of a crazy set like this one. What's interesting about this Cantor set is, believe it or not, it has length 0. Okay? Its measures, the way we call it. We say C has measure 0. And one way to say that, I'll informally define it here. It can be covered for any epsilon, for any positive number epsilon, it can be covered with sets of size less than epsilon. For any epsilon, for all epsilon bigger than 0, C can be covered by intervals of total length less than epsilon. It's an amazing fact about the Cantor set. Uncountably many points, but length 0. Okay. Very, very cool. Good. So that's an introduction to Cantor sets. They pop up in all sorts of places, and don't be surprised if they pop up in our class as well. Okay, and on your homework, for instance. Okay, if you've looked at your homework, maybe this might give you a hint as to what to do with one of your homework problems. Okay, while I'm on the subject of the homework, I do want to mention one other thing about about the homework, which is a concept that's defined in your homework. One of the problems talks about a base for a metric space. And I just want to give you some intuition about why we care about a base. Actually, that's Rudin's terminology. The more common terminology these days is the word basis. Okay? And how many times have you heard the word basis in a math class? What is a basis for a vector space? Okay, lots of ways to describe it, but the operative concept is a basis you build other things from, right? You can build any vector as a combination of basis vectors, right? Okay, well, this is exactly the same, analogously the same concept here. What is a base or a basis for the open sets or for a metric space? Of course, this is the way we describe it in topology. It's a basis for the topology. It's this. You give me any open set, let's call it U, and any point in it, let's call it X. A base, is a collection. It's some collection. And I don't care what collection it is, but it's a collection that has the following property. You give me any open U, and any point x inside it, what's true about a basis is there's a point of the basis that surrounds x that's inside of U, such that what? For all x in some open U, there exists a V alpha such that x is in V alpha and V alpha is contained in U. For any x in any open U, there is a V alpha such that V alpha lives in between. Okay, now what's the big deal here? Well, the big deal here is I can do this for every point in U, yes? So U can be written as the union of a bunch of basis elements, just by taking the union of V alpha for every point x. With me? Yeah, so in fact, the idea here is, so every open set is the union of base elements. Okay, and your homework asked you to explore this concept. And really, the reason is that there's all these concepts that have to do with the size of a set. So if you have a metric space where the base is countable, then it's small in some sense. If you have a metric space that has a countable dense subset, in other words, separable, which you learned in your homework last week, then it's small in some sense. Okay? And it turns out that if you have a metric space that is compact, well, then in fact, a compact metric space has a countable base. Compact metric space has a countable dense subset. Okay, so these notions of smallness somehow coincide, and they give you other tools for showing that a space isn't compact, right? If you know that a compact metric space has a countable base, and you find a metric space that doesn't, then it can't be compact. Right? Other strategies for showing not compactness. Yes, Jenny? Oh, well, yeah, so this has got to be true for any U, for any open U, right? So, yeah, for any open U. And in general, for a topological space, in order to be a basis, you need it to have the property that there are enough small sets to take care of things. So you want it to be the case that if you intersect two V's and you take a point in between, that there's another smaller basis element inside. The way that you would make that true here in a metric space is demand that these V alphas be themselves open in the sense of having interior, every point being interior. Okay, so the idea of a basis is basically you can build up all open sets from just these. Okay. Now, one basis for a metric space is just to look at balls. That's a basis. We've already seen that. But you could also take other things to be basis elements. Okay, that's a word about bases. Okay, let me say something about connected sets. As I hinted at that here. Yeah. Excellent question. No, there's not a general notion of you can't talk about something that is the smallest basis because they don't necessarily, one small thing doesn't necessarily contain the other, etc. Yeah, so you can't intersect two bases and hope to necessarily get a basis or anything. But there could be lots of different bases for a particular metric space. Yeah. Okay, great. This is the last concept I want to discuss today, and that is connected sets. What does it mean for a set to be connected? So, for instance, if I draw a picture like this, does this set feel to you somehow connected? Yeah, sure, right? But what about this one? Not connected, right? Why? How do we make that notion precise? Well, it turns out it's a lot easier to say what's not connected than to say what is. And I'll show you why. What's true about this set not being connected? Well, somehow I can separate one from the other, right? Yes?
Visually right there with that particular set, it has a finite open cover where the pieces of the open cover have an empty intersection.
Okay, I think
So
you're...
we can cover with disjoint sets.
This is sort of what you're saying, yes? These are open, and they separate the two. Yes? Okay. And that would rule out, like, this picture. Can't I cut this piece into two pieces where this goes in one half and then the other half doesn't contain this boundary? Well, I certainly can cut those into two pieces, but you wouldn't want to call these separated either, right? And your criterion would prevent that, right? You can't put an open ball around this and an open ball around this that don't touch each other. Yes? Okay, good. This is actually a good topological definition for separated sets. The book uses a different notion, which is equivalent. And the equivalent concept is you demand, let's say this set is called A and this set is called B. We'll call A and B separated if no point of A is a limit point of B, okay? And vice versa. That's actually, can you see why here that's not true for this A and B? Isn't it true that some points of A are limit points of B, especially if I go from this side towards the boundary? Okay. So that's the concept of separated. So let's make that definition first. So if A and B are, we'll say two sets A and B in X are separated if you're going to demand both of these to be true, A intersect B closure, and A closure intersect B are empty. This is saying exactly what I just said, namely, no point of one is a limit point of the other. Okay? Happy with that? This is what it means to be separated. And now we have that notion, we can say what it means to be connected. We'll say a set E is connected if E is not, what? Good. Is not the union of two separated sets. Okay. If you have two separated sets, what do you think we call them? We call this a separation. Okay, not surprisingly. So if you can't find a separation of E, then it's connected. Okay? And so these examples give a clue as to what that means. So let's test our understanding here. What about this example in R2? Let's look at the set E of all rational points that pairs x, y, where x and y are in Q. Is this set connected or not? Set of all rational points, which look like, I don't know, come on. Is it connected or no? No? If you say the answer is no, you have to give me a separation. Find me two sets none of whose closures intersect the other. Can you find one? Oh. How many people think this set is connected? How many people think it's not connected? Then how come you guys aren't giving me a separation? You just have to find two sets. Well, let's see. Would it be okay if I put axes on this? Okay, but there's lots of points on that line, so that wouldn't be a separation. Okay.
So let's kind of set to have x and y are strictly greater than 0 and strictly less than 1.
Okay.
And then another set where x and y are both strictly greater than pi and strictly less than 6.
No, because we want the separation to be one whose union is the whole thing. And if you do the less than or equal to y and greater than y, it turns out that this is not true because their closures include the diagonal. Okay, nice tries though. Let's. What about this one? Suppose I look at the point pi here. Would you agree that the line at pi has no such points on it? So let's let this side be A and this side be B. Its union is all of E. That is, A is all the points on this side, B is all the points on this side. Union is everything, right? In E. Brian's saying yes, that's good. Can you see why A closure doesn't intersect B? Yeah. Any point on this side of the line can't be a limit point of this side because it has a ball around it that completely avoids this line. If A has any limit points, they'll be on this line, but they won't be over. Okay? So notice the limit points of both sides can actually intersect, but here we only demand that one does not intersect the closure of the other. That's why this definition is important. Now, coming back to this picture, what that means is you actually can allow the open sets to overlap, but they can't do so in points of E. So another way to say that is this characterization is true when you think of E and you use the relative topology on E. That is, you think of E as the whole space. Okay? So I'm going to mention this even though it's not mentioned in your book, and that is another definition is E is connected if in the relative topology, in the relative sense, if E is not the union of two closed or two open sets in E. That is, in its own, if you're thinking of this as its own space. By the way, if it were the union of two open sets in E, then what would the complement have to be? The other set, and it's closed. So another way to say it is E is connected if it's not the union of the same definition with two closed sets in E. This is all in the relative sense. Relatively open, relatively closed. Okay? But if you're viewing it as embedded in a larger space, then you have to use that definition. Okay? Okay. So now the final question is, do we know any sets that are connected? Name one that you think we might want to decide is connected or not. Is the real line connected? What do you think? Can we show that? In fact, let's show something that's maybe a little smaller. What about just the set 0, 1, or the set AB? An interval. You think it's connected? How many people say yes? Yeah, you're right. It's connected. Let's do a proof. And as these proofs go, to show something connected, it's a lot easier to do it by contradiction. Why? Because if it's not connected, there exists a separation, and you can work with that. Okay? So, here we go. Proof. If not, then there exists a separation. I'll abbreviate separation. Let's say A and B. Okay? With, let's just put little a and big A. So here's the interval, little a and b. And here's a set. Whatever the set is, maybe the set, who knows? I don't know what's true about these sets A, but maybe big A is like, who knows? Maybe it can contain several different pieces. I don't know. And let's say B, the other set B, contains several different pieces. Okay. And by the way, this set A could contain this endpoint B. I don't mean to indicate that little b necessarily is contained in big B. So what's wrong with this picture? We're trying to get a contradiction. What's true? A closure does not intersect B. B closure does not intersect A, yes? So we got to find a contradiction here in this picture. Where would you say would be good to look, a good place to start? Yeah, some endpoints here, right? So let's do that. That's a great idea. So Rebecca said, let's look at an endpoint. How about this endpoint? Let's look at, how about the rightmost point of A, otherwise known as the supremum of A. Love that idea. I'm glad I thought of that. Okay, excellent. Yes, it is okay. Let's just see how to modify this proof if that happens. Okay, excellent thought. So let's let S be the supremum of A. Then, what do we know about the supremum? Well, it's got to be in a closure, isn't it? Because either it's in the set or it's a limit point. It's approached by the points in A. Yes? Mm-hmm. Oh, yes. Sorry, these are non-empty. Thank you. Yes. Sorry, so coming back here, the question was, shouldn't these be non-empty? And the answer is yes. Okay. And actually non-trivial. So it's non-empty, not the whole thing. So maybe so by non-trivial, I mean can't be empty and can't be the whole thing. Otherwise, the other one would be empty. Okay. They're automatically separated in E. So if you just restrict yourself to E, the fact that they're both open means that they're also both closed, and therefore they're both clopen in E. And therefore, the closure of this set, of the set in E, is just itself. And so it will never intersect the other set. Okay, so this is all taking place in E in a relative sense. Okay, so if they're both open, they're both closed, and they're both clopen in the set. Okay, it'll take a little thought. For the most part, we're not using these definitions. I'm telling you this for culture because you'll encounter this in topology if you take topology. in the real line, we usually use that definition because we think of this set as being part of the real line rather than existing in and of itself. Okay, so back to this proof. If S is a supremum, let S be in, then S is got to be in a closure, right? Because either it's in the set, or if it's not, then it's not anything smaller must be not an upper bound, so there has to be a point very close to the supremum. In your book, this is 2.28, and we did show this in class as well. So if S is in a bar, then what this means is this last point is actually in a closure. Therefore, it's not what? In B. Okay, so if S is not in B, then where is it? Then it must be in A. Dot. Oh. But if it's in A, we're still trying to get a contradiction. What's the contradiction? If it's in A, then it's not in B closure. By definition of separated, using the other condition. So if it's not in B closure, what does that mean about this point, this red point? It has an interval around it that completely misses B. Oh. Then there exists an S minus epsilon and S plus epsilon, not in B, containing no points of B. Oh, but A and B are the whole set, right? So this interval must be where? In A. Hence, all in A. But why is that a contradiction? Because S is the supremum. But this contradicts S as supremum of A. Okay, let's answer Laura's question as to how you would modify this proof if, in fact, the endpoint were, if sup A was B. You would not get this contradiction anymore because there isn't anything beyond. And so this interval, well, it's still fine because there's nothing on to the right-hand side in the relative topology. So what could you do, Emil? Yeah, you could use the infimum of B. Okay. So fix this as appropriate if it's not the right-hand endpoint. Okay.
Could you just start out by saying, like, what is the infimum of B and just start from there?
Yeah, this probably could have just made this a lot easier by just looking at the infimum of B. Or I could have started with the set that doesn't contain B. Yeah, very good. Okay, that's a good place to stop. With the remaining 5 minutes or so, I'd love to get your feedback about this course and how you're doing and how I'm doing, etc. Thanks. Next time we're going to start talking about Chapter 3, which is sequences.